Now Samriddhi will give some tutorials for the new users. Samriddhi, please.
My screen is visible.
Yes.
Okay, so this is the tutorial sessions for the new users. So I'm presenting it for this meeting 2022. First of all, so what is the pencil code? And after 4 days, we already know that pencil code is a higher order finite difference code for compressible hydrodynamic flows with magnetic fields and particles, and it is modular and can easily be adapted for the different types of astrophysical problems. It's parallelly shared and distributed memory code, and it is an MPI. So this code is was originally developed at the Terminal Summer School, as PLD already mentioned, and on 2015 the code is moved to GitHub. It was previously hosted in the Google code. So to run a pencil code, we need a Unix-based system. It may be a Linux or a Mac, and Fortran and C compiler. It may be G-Fortran or iFortran or anything you'd like, or GCC or ICC for the C compilers. We need MPI wrapper script for parallel programming, maybe OpenMPI or MPI CH2, what you prefer, and a visualization tool, for example, Ideal, Python, Paraview, or Mathematica. But mostly, except this, we also need the main thing, the pencil code. So I will show you how to download the code for this session, and in the next session, I will show a sample and to visualize the results too. So I am closing this presentation and sharing the terminal. I have a pencil code already installed, so I am making a new directory, PCUM22, and then I am going to that directory. This directory is empty, so so if we check the procedure to download the latest version of the code, one might use SVN or Git, but for this session I will use Git. And to install the code, you have to check that Git is already installed in your computer or not. So for that, you have to put Git version. So if it shows Git version, then you have Git installed. Otherwise, you have to run two commands. One is sudo apt install Git for Ubuntu or Mint, or for Mac, it's do install Git. You have to install do before this command. And once you have installed Git, then you have to clone the repository. And the link of the repository can be, you can got from the Google pencil code GitHub. So it will show the GitHub page. And if we go to the pencil code, you can get that code link, that HTTPS GitHub pencil code. So just copy this code and you write git clone, paste, and enter. It will take some time, and after that it will download it in your computer. You don't need any GitHub account to download it, but for checkout or committing any code or any modules, you need a GitHub account for this, but not for downloading or using it in your own computer. So it takes that time, no problem. And in that time, I will show some more things. Okay, so this is the hands-on session. So I will show after it completed the downloading process. It's Any questions in that time? If any new user in the group or the meeting not installed pencil code yet.
If there are any new users who have not installed the pencil code, they can just parallelly go ahead and do it. So that you will also get the practice. Yeah, so for later tutorials, we will going to show about certain diagnostic tools. So if you have the package, then you can also go back and refer the code.
So we already installed the pencil code. So we go to the pencil code directory and we can see few folders and sourceme.sh and sourceme.csh. These two folders are actually important to link the pencil code path to the path of your bash script or the ch script. So for this we will do sourceme.sh. Okay, so the path is actually linked to your actual bash path. And I will also say something that there are some visualization script and the helping script. So helping script are always in the bin directory, and the visualization script is actually in the ideal directory. Config contains the compiler configuration, default and personalized configuration, and Julia, Python, IDL, and Mathematica are the visualization folder. It contains script for visualization. The SRC is the source code folder. It contains all the F90 source files. So if we go to vim eq.f90, it is the actual Fortran file which calls that your continuity equation, the Navier-Stokes, the energy equations, or this is in the PD subroutine. So if we go PD subroutine and search something called DLN row underscore DT, this is the continuity equation. So from the PD subroutine, this continuity equation is actually called, and before it, the MN block is situated in this file .f90. So every time at every pencil, this DLN row DT is called, and the actual code is in DLN row DT is in the density module. If we check vim density.f90, it contains that DLN row DT part. So this is the actual subroutine which calculates the continuity equation. And there are some flags like it's L continuity gas or L density no log. So if you remember Sohail Dev's tutorial, he showed two equations. So one is DLN dt and one is d rho dt. So if you want use density rather than ln rho, so you have to turn on this flag n density no log, then it will calculate d rho dt. But so ug rho is actually the u gradient u dot rho. So these are calculated in the derive.f90 module. The actual gradient or the gradient or the curl, these mathematical process is done in the derive.f90. So, so this is the actual folders or the files you will get. To start your work, you have to create a own working directory. For this, you can do mkdir workdir. Then we will go to the directory ct workdir, and there is no file since you just created it. as PLG told that to run a code, you have to choose a sample which is nearly to your problem. So today we will show a Kelvin-Helmholtz case. So Kelvin-Helmholtz code or the samples are in the samples folder. If you go and Kelvin-Helmholtz, you get 2D problem. So we go 2D test, sorry. And in this case, we got these this one, Kelvin-Helmholtz. We can go CD, Kelvin-Helmholtz. So these are the files. So we have to copy these to our working directory. And the process is simply, you can do it with any command. So CP minus R, pencil code, and then samples, and then 2D test, and then Kelvin-Helmholtz, and this. So this is the Kelvin-Helmholtz folder you copied from the samples. Please don't change the samples, because if anything happen to the sample, then you have to re-download your code, and it also takes some time. So just copy it in your working directory. And in the directory, you can see few files and a directory. That directory is the SRC. And if you check, the files are start.in, brand.in, print.in, readme, and reference.out. So reference.out is present because this is an auto test file. So if anyone in the developer changes some code, then pencil code actually checks it, and it will matches a previously stored value. So reference.out actually contains the correct value. So if after the changing of the code, something happens and it does not equal to the reference.out, then that commit is not succeeded and it is aborted. So it's, and in the SRC, there are two files, which is makefile.local and the cparam.local. So if I open start.in, it actually contains the initial parameters or the startup parameters. So LPD is the periodic logic flag. So it is TTT, means in all the 3 dimensions are periodic in this case. IP is the verbose comment like thing. So if it is 1, then there are lots of diagnostic output, and if IP is 14 or more, it will show less diagnostic output. And LWrite aux means it can create some auxiliary files. I will show in this case that what is the auxiliary files in this case. And LWrite and XYZ0 and LXYZ is the corners of your box, of your simulation box. So 000 is the first corner and 111 is the last corner. So it's a 1 unit of your box, Cartesian box. CS0 is the sound speed, and gamma is the gamma gas gamma CP by CP. And L density no log equal to 2, since I already told that pencil code can calculate time evolution of ln row as well as row. We will take row in this case, so we turn on this flag. And this is the initial conditions, else move 0.025. We will figure it out when we go into the makefile.local. In the brand contains the brand time parameters, or so in this case NT. These are the most important thing in your brand actually. So NT equal to 50 means the code actually brands up to the 50 times. IT1 implies IT1 equal to 5 means that it will print your diagnostic output after every 5 time step. CDT is the advection Courant number and CDTV is the diffusion Courant number. I say equal to 100 means it will store your last snapshot after every 100 time step. IT order 3 means it uses the third order Runge-Kutta method for that time stepping. Dsnap equal to 0.02, it implies that at every 0.02 time units, it will store your var. It will store your snapshot. So there are two terms. One is time step, one is time unit. So NT means time steps, and the snap actually uses time units, not the time step. We will figure it out what it actually means when we actually run the code. And IP is similarly the verbose or the anti-verbose line. It will show your diagnostic output. L pencil check is F means that when we run this sample, it will not check the pencil code. So inside the pencil code, it actually checks few samples if it is correct or not. So we turn it off actually. Tmax equal to 1.5, it means the code will stop if the time hits 1.5 time units, not time step. And NT and Tmax, NT means time step. So if the code hits 50 time step, the code will terminate. On the other hand, if the code hits T is equal to 1.5 time units, it still terminates. So we can have which one is earlier. There are some other parameters which we will check when we run the code. I will write all these things to the slide. So if we check, so we already go into the pencil code by CD pencil code, and we have to source the source me.sh, which actually add the pencil path to your bash script or the ch script. Then we have to create your own working directory. In this case, it is whatdid or any file name. And then we have to set up a sample by cp-r sample.any file in your working directory. We already told that there are few files like start.in, which contains the startup parameters, geometry, and units. In this case, we have not mentioned the geometry and units, but by default, pencil code will choose the Cartesian geometry. Brand.in contains a brand time parameter. It also contains the boundary conditions. As you know, it's LPD, the flag, which actually choose the boundary conditions, and the time step and the time units, like in NT or dsnap, ISET, these things. Print.in contains the diagnostic variables to print. I have not opened that file. If we open print.in, it will show these few parameters that actually helps you to diagnose your code. So IT is the time step, T is the time units, DT is the time step in time units, rho max, rho m. These parameters are mentioned in the manual in the print.in section. So if you go to the manual and open it, it will list you lots of diagnostic output, which helps you to understand when the code is running, if it is correctly doing the job or not. So, and from the other thing, print.in, and the local files are cpanam.local and make file.local. We will go into src, and if we open it, we can see the two files. These two files actually only for your local directory. It is not present in the any other directory except your working directory. If you open cpanam.local, it contains your CPU configuration or CPU configuration and the grid size thing. So n CPU is equal to 4. It means that we are using total of 4 cores. And nproc y and nproc x2, it means that to solve your problem, pencil code uses 2 nproc and in x direction and 2 proc in y direction. And nproc z is equal to n CPUs by multiplication of 2, which is equal to 1. So when you set up your code, please be sure that nproc x and into nproc y into nproc z is equal to your n CPUs. Otherwise, pencil code will not run. And nx grid equal to 32. It means that we split our x domain, x grid, in the 32 subdomain in a small 32 parts. and ny grid equal to nx grid. So it means that ny grid also 32, which actually splits the y direction in the 32 part. And since the two-dimensional problem, since nz grid will equal to 1, we have to set one single grid in the z direction if it is a 2D test. So if it is 3D test, then nz grid will be 2 or something. I mentioned that in the presentations too, that CParam contains parameters like CPU numbers and the grid sizes per direction. Also, as you, if you remember in the soil stock or the Hongqi stock, they told the auxiliary variables. So those variables can be mentioned, should be mentioned in the plan.in file. In our case or in this session, there are no auxiliary files that we have to explicitly mention. So that's why we have not seen any MOX contribution in the cparam.local. But if you using a magnetic module and want to calculate the magnetic field or the current density or some vorticity in case hydro, then you have to mention it in the cparam.local using MOX contribution. So if you use a magnetic field, it has 3 components, so MOX contribution should be 3. Now we will go to the makefile.local. It contains your module you need for the code and also some precision flag, and it is an MPI job or not. So it is an MPI job since CPU in the cparam.local we choose 4 CPU cores. That's why MPI-com is equal to MPI-com. If you use single core, then it should be no MPI-com. We use these modules since it does not contain any magnetic thing, so it is no magnetic. We don't use gravity in this case, no sphere, but we also use SOC and SOC higher order. So if we go to the SRC, actual SRC, then you can get a file name SOC higher order.f90. In this case, we choose this initial condition, which is already saved in the Kelvin Helmholtz, and the real precision is double. So if you are a new user, just to do these things in the meantime, we will show in the next session to run a code, run the Kelvin Helmholtz sample successfully, and to visualize the actual thing, the Kelvin Helmholtz visualization, we will do in the next session. And if you have any question in the meantime, just you can also ask it now, or put it in the Slack or in the Zoom session, in the Zoom chat box.
Thank you, Samriddhi, for this. This is very much useful. Your hands-on sessions are. So now new user understood that how to download the code and how to how the other files like in file, local file, and other modules, how these are working. And this is a very nice introduction for the new users. If you have any questions, then kindly raise your hand.